Hello everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to start with the chapter P block elements, and we are going to start since we know what is P block. We've already studied the periodic table chapter and we've seen that P block elements are going to be from group 13 to group 18. So firstly, we are going to start with group 13 elements, and that too will involve a lot of properties that we have to study. So when I talk about group 13 elements, we need to talk about in this particular lecture, we will be discussing the electronic configuration, the abundance of these elements and their physical properties. And likewise, we'll be talking about chemical properties, etc. in the upcoming lectures. And once we are done with group 13 elements, then we are going to move on to the next group. Okay. So before we begin, a piece of information for you. You can use the coupon codes Mission J or Mission NEET while you enroll at First Online University for Mission J or NEET in order to avail good discounts. Let's first begin with the introduction and electronic configuration of Group 13 elements. Now, when we talk about Group 13, first of all, we need to know what are the elements that are present in Group 13. So first is boron, aluminium, gallium, indium, thallium. These are the 5 elements that come in the group 13 elements category. And when we talk about these elements, they are placed in group 13 in the long form of the periodic table. So if you look at the electronic configuration of these group 13 elements, which are also known as group 3A elements, it's going to be boron. Since we have seen that boron has got 5 electrons, it's going to be 1s2, 2s2, 2p1. Now, since they are p block elements, the differentiating electron is going to enter into the p subshell or the p orbital, and therefore the electronic configuration of all these elements is going to be going into the p subshell. But since we are talking about group 13, which is the first group of the p block elements, therefore each of these elements that we are going to discuss will have np1 configuration, where n is going to be the period number. That is also the principal quantum number. Okay, so now when we talk about boron, since it is present in period 2 and it has atomic number 5, so it's going to be 1s2, 2s2, 2p1. That's the electronic configuration of it. Next, we talk about aluminium. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p1. So now it's going to be like 3p1. Similarly, so 3s2, 3p1, 2s2, 2p1. That is the valence shell electronic configuration which we are interested in knowing. Then when we talk about gallium, the atomic number is 31. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. So now it's going to be 4p1 and d orbital also comes into picture now. So the next is indium 49. So whatever we have done till gallium, that is 3d10, then 4p6, 5s2, 4d10, 5p1. That's going to be for indium. And lastly, for thallium, what we have is, now here apart from 3D, 4D and 5D, 4F is also going to come into picture, and the outer shell electronic configuration is going to be 6s2, 6p1. Okay. Now, their general outermost electronic configuration is ns2, np1. We've already seen that. So if we talk about the element atomic number and electronic configuration, that's going to be like the first one is boron, atomic number 5. And we are going to write down in terms of the noble gas configurations now. So whatever the nearest noble gas before that element is, we'll put that and the rest of the configuration along with it. So when I talk about boron, it's going to be helium 2s2, 2p1. Then we talk about aluminium, that is going to be neon 3s2, 3p1. Then gallium is going to be argon 3d10, 4s2, 4p1. Then indium 49 is krypton 4d10, 5s2, 5p1. And thallium 81 is xenon 4f14, 5d10, 6s2, 6p1. These are the electronic configurations which you need to remember, not the entire ones. Okay, this is all that you have to remember. So you do not have to go into details of learning all these long electronic configurations. Just these short ones are sufficient for you to know. Next, we talk about a few MCQs now. Let's do a few concept check here. So the first question is general electronic configuration of 3A group elements, that is group 13 elements, is what? Your options are Ns2Np2, Ns1Np2, Ns2Np1, or Ns2Np3. So we have already seen that it is the first group of the p block elements, and therefore the general electronic configuration will have completely filled s subshell, and there is going to be just one electron present in the p subshell. Therefore, Ns2Np1 is the general electronic configuration for group 13 elements. So option C here is the correct answer. Next, we talk about the abundance of group 13 elements. Now, when we talk about abundance, means how are these elements and in what quantity are they available? When we talk about their presence on the earth, okay. So, if we talk about boron, boron is a rare element and it mainly occurs in the combined state. Okay, it has two isotopic forms, that is boron 10, which is 19% in abundance, and boron 11, which is 81% in abundance. The important minerals of boron include borax, that is Na2B4O7.10H2O. Then we have kernite, that is also known as razorite, that is Na2B4O7.4H2O. Then orthoboric acid H3BO3, and colemanite, that is, since see how you can do is like borax is the most important mineral of boron. Then we can talk about kernite is also important. When you talk about colemanite, since it starts with C, so remember that it has calcium in it. So Ca2B6O11.5H2O is going to be the formula of this important mineral of boron. Next, we talk about aluminium. Aluminium is the most abundant metal, and third most abundant element in the Earth's crust. These are two important facts that you need to remember. You can get direct MCQs based on this. Then, important minerals of aluminum are corundum, that is alumina, Al2O3. Then we have diaspore, that is Al2O3.H2O, bauxite, Al2O3.2H2O. Okay, so easy to remember. Just one and then another water molecule of crystallization is being added. Then gibbsite is Al2O3.3H2O. Then we have cryolite, that is Na3AlF6. This is something which is different from the rest. And then we have feldspar, which is K, that is potassium aluminium Si3O8. Okay. See, I have taken up only the most important minerals from all of these elements. So you cannot just leave them like that. You will have to remember these. Okay. That is the molecular formula of them. Now, when we talk about gallium, indium, and thallium, they are less abundant in the Earth's crust. They are also highly toxic, and therefore we're not going to go into details of them. So, if we look at the decreasing order of abundance, aluminium we have seen is already the most abundant metal, and it is the third most abundant element in the Earth's crust. Then followed by gallium, followed by boron. Then we have thallium, and lastly indium. So this is the decreasing order of abundance of these elements, that is group 13 elements. Next, and if we want to talk about their percentages also, the percentage abundance of these elements, we can have a look at these quickly. So if we see here, it is aluminium has the abundance of 8.2%. Then gallium is 0.0018%, that is just 18 ppm. Then boron is 10 ppm, thallium is 0.6 ppm, and indium is the least, that is 0.05 ppm. I think it's not visible to you, but I'm just telling you it's 0.05 ppm. So a question for you is the number of water molecules present in borax. We've already seen the formula of borax. It has 10 water molecules of crystallization. So option D is the correct answer. Next question is formula of corundum. So we have already studied corundum was the first mineral that we studied, and it had no water molecule of crystallization. Option C is the correct answer. Next question is formula of cryolite. Again, we have studied what is cryolite, and we know that it is both A as well as B, because it's like the same thing. Okay, 3 sodium being present. 3 NaF means 3 sodium and 3 fluorine here, and then there are 3 fluorine there, so total 6 fluorine. 3 sodium and 1 aluminium. That is the formula for cryolite. So both A and B is the correct answer to this question because we can write them in both the form. Okay. Next, we move on to the physical properties of group 13 elements. Okay. Now, when we talk about the physical properties that we are going to discuss are atomic mass. The first is atomic mass. So when I talk about atomic mass, we know that as we go from top to bottom in the group, the atomic mass is going to increase because the size is increasing. So when we talk about the atomic mass, so from boron to aluminium to gallium to indium and lastly thallium, what we have is the increasing order of atomic mass. Next is atomic radius. So we know that as we go down the group, the atomic radius or the size is going to increase. But there is an exception that we see here. As we go from aluminium to gallium, the size is decreasing. That is, gallium has got a smaller size in comparison to aluminium. Now, what is the reason for this? That is because of the screening effect of the electrons of the penultimate shell. Now, first of all, what is penultimate shell? The last or the outermost shell is the valence shell, and the shell just before the last shell or the outermost shell is known as the penultimate shell. So whatever electrons are present in the penultimate shell, they show a very large screening effect. Screening effect means that these electrons are going to prevent the nuclear pull or the pull of the nucleus towards the outermost electrons, and therefore the outermost electrons are not going to be attracted to the nucleus to the extent that they should have been. And because of this reason, the size is not getting decreased, it is actually increasing only. So but that is not the case with gallium, and therefore aluminium has got a larger atomic radii as compared to gallium. So what is screening effect? We have already seen that is the decrease in the force of attraction of the nucleus over the valence shell electrons because of the inner core electrons shielding. That is called screening effect, and greater the screening effect, easier is the removal of the outermost electron. Next, we talk about ionic radius. Since we have already seen atomic radii, the ionic radii is also going to show the same order. That is what we expect. Now, when we talk about ionic radii, we first need to know that when the ion is going to be formed, what is going to be the charge on the ion. Since we have already seen that the electronic configuration of group 13 elements is Ns2Np1. So there is a possibility of +1 oxidation state when 1 electron from p subshell gets removed, and there is also a possibility of +3 oxidation state when 1 from p and 2 from s are going to get removed. That is, when ionization potential is going to be applied. Then we can also have +3 oxidation state that is possible. So here what we know is that when we talk about the ionic radius, we are talking about the +3 oxidation state of these ions that are being formed. So ionic radius increases from top to bottom. So when we talk about, that's what I told you, right? Just as we have the order for atomic radius, similar is the order for ionic radius also. So as we go from top to bottom in the group, the ionic radius is also going to increase. And the order is going to be boron 3+, aluminium 3+, gallium 3+, indium 3+, and thallium 3+. That is going to be the increasing order with no exception in this case, because the outermost electrons are already removed. So the screening is not going to be for any electrons, right? Since no electrons are being shielded, the size order is going to be without any exceptions. Next, we move on to ionization enthalpy. Now, ionization enthalpy value is going to decrease as we go down the group. That is with the increase in atomic radii, because when the size is going to increase down the group, the pull of the nucleus towards the outermost electrons is going to decrease. And when that pull decreases, it becomes easier for these electrons to actually get removed from the atom. And therefore, we can say that ionization enthalpy decreases with the increase in atomic radii. So you can see when we have the atom, the electron is removed, we have a positive charge, that is monovalent cation. Another electron removed will give IE2 value, and that is going to be the +2 charge, that is divalent cation. Okay, that is how we get. So the order of ionization enthalpy we have already seen is going to be IE3 greater than IE2 greater than IE1. So that's going to be the correct order. So from boron to aluminium, the ionization enthalpy decreases, but from aluminium to thallium, it marginally increases. Okay, so if we look at the values, okay, I'm not just talking in air, we have the values for ionization potential. So from boron to aluminium, it decreases, but from aluminium to gallium, you see there is an increase just by 2 units, but there is an increase. Again, when we talk about indium, there is a certain amount of decrease, and then to thallium, it again increases. So if we see, there is no specific order that is being followed, but on a whole, superficially, we can conclude that from aluminium to thallium, the values are marginally increasing. Okay. So if you look at the correct order, that is the exact order, it is going to be boron, then thallium, then gallium, aluminium, and indium. That is going to be the decreasing order for ionization potential based on these values that have been given through experiments. And therefore, we can say that boron has the highest ionization potential when we talk about group 13 elements. The observed discontinuity in the ionization enthalpy between aluminium and gallium and between indium and thallium. All these exceptions are owing to the screening effect of DNF orbitals. Now you will say, how come screening effect has come into picture all of a sudden? That is because of the presence of D block and F block. D and F electrons. Okay, so these D and F electrons are very effective in showing the screening effect, because these electrons are large in number and they are going to prevent these the nuclear pull to be attracting the outermost electrons, and therefore we can say that the screening effect is going to be lower because of these D and F orbitals being present. Okay, next physical property that we are going to talk about is electronegativity. Now, what is electronegativity? The tendency of an atom to pull the shared pair of electrons towards itself is known as electronegativity. Now, electronegativity, as we talk about electronegativity trend from boron to aluminium, the electronegativity decreases because down the group as we go, the size is going to increase and the tendency to pull the shared pair of electrons more towards itself is going to decrease because electropositivity increases. But when we talk about aluminium to thallium, the electronegativity is going to marginally increase, just as we have seen the case of ionization potential. So if you look at the values, you will see that from boron to aluminium, it is decreasing. But from aluminium to gallium, and then gallium to indium, and then indium to thallium, the values are slightly increasing. So boron, then thallium, then indium, then gallium, and lastly aluminium, that is going to be the decreasing order of electronegativity. And for we can say that boron is the element that has got highest electronegativity value. Next physical property is melting point. Now, boron is extremely hard and it is a black colored solid. It's not boron, it's boron. Okay, so that's a typo error here. Then when we talk about the melting and boiling points of boron, they are very high because boron is very hard and it is also small in size. The order of melting point is therefore going to be, if we talk about these values itself, we see that from boron to aluminium, it decreases, drastically decreases. Then from aluminium to gallium, it further decreases. Then from gallium to indium, it is increasing. And then from indium to thallium, again, it is increasing. So what do we see is that since there is no particular trend that is being observed, but we can say that boron has the highest melting point and gallium has the least melting point or the minimum melting point. And we can also talk about the order. So boron maximum, then aluminium, thallium, indium, and lastly gallium. See, sometimes you are asked questions based on order, so you need to know. But more importantly, you need to know which has the highest and which has the lowest melting point. So that is because of the strong. So why do we have these exceptions that are being observed? That is due to strong crystal lattice. Boron is having a high melting point. The crystal lattice being formed is so strong, it is so hard that it is very difficult to break the crystal lattice and get the element from the solid to the liquid form, and therefore a lot of heat in the form of temperature is required, and therefore melting point is higher. Gallium has low melting point and it exists as simple Ga2 molecule. Next, we talk about the boiling point. The order of boiling point, if you look at the values itself, boron maximum, then for aluminium it decreases. For gallium further decreases, indium further decreases, and thallium is the least. So if you see, the boiling point has a natural order. That is, as we go down the group, the boiling point is decreasing. There is no exception in between. Maximum is boron and minimum is thallium. Simple. So now make a note of the fact that due to large difference in temperature between the melting points and boiling points of gallium, we use it as a pyrometric liquid. That is filled in high temperature measuring liquid thermometers. Now whatever liquid thermometers we have, that is high temperature measuring liquid thermometers, we make use of gallium because it has got a very high melting point and a difference of 2373 Kelvin in the melting and boiling points. So when we have to measure very high temperatures, we make use of gallium in that liquid thermometer. Next, we talk about density. Now, when we talk about the density of group 13 elements, as we go down the group, the density is going to increase. We can also have a look at the values here. For boron, aluminium, and all these elements, we are talking of the density in the solid state and then in the liquid state. So when we look at the values, we see for boron, aluminium, gallium, indium, and thallium, the order is going to be, what do we see is that down the group, the density is increasing with no exceptions present. Okay, for the solid state, it's different. For liquid state, it's different. Next is electropositive character or metallic nature. So we can talk about both these properties simultaneously. So we know that as we go down the group, the electropositive character or the metallic nature increases, but from boron to aluminium, the metallic nature decreases, okay, but from boron to aluminium, the metallic nature is actually increasing. Okay, that means that aluminium is going to be more metallic in nature than boron, and therefore we can say that the order here is going to be first aluminium, then boron, then gallium, indium, thallium. That's the natural order with no exceptions. Now let's quickly have a look at few MCQs. Which group 13 element has lowest melting point? We have already seen that it's gallium that has got the lowest melting point. Next is the order of electropositive character of group 13 elements is. So we have already seen that down the group, electropositive character is decreasing. But there is this exception at the boron aluminium interface. That is for the aluminium is going to have a higher electropositive character, and therefore here option C is going to be the correct answer. Yes, indeed, that's the answer. Next question is, which group 13 element is used as a pyrometric liquid? We have already seen that there is one particular element that has got a difference of 2373 Kelvin between the melting and the boiling points, and therefore it can be used as a pyrometric liquid. That is gallium. So option B is the correct answer. So this is all about the introduction to group 13 elements, the abundance of group 13 elements, their electronic configurations, and their physical properties. In the next lecture, we'll be taking up the chemical properties of group 13 elements. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app through Google Play Store or App Store for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.